Welcome to the PhotoModeler Automatic Tools tutorial. This tutorial demonstrates the use of several tools that automate marking and referencing in points-based projects. Part of the tutorial uses the optional Coded Targets module. For more information on the Coded Targets module, visit the PhotoModeler website. The latter part of the tutorial reviews methods that are applicable with and without coded targets. In this example, we have created some high-contrast circles using a laser printer. The coded targets were created using the option under the File menu. You can use any form of high-contrast circle, paper, stickers, magnets, or even projecting them using a slide projector as long as the circle has a high contrast with its background. In this case, instead of cutting the circles out, we left a white border to ensure high contrast regardless of the background color. If your object was a solid color, you could apply circles directly to it. For example, white dots stuck on a dark blue car panel. The target should be no smaller than about 10 to 8 pixels across in the final photos. Their physical real-world size will depend on your camera's focal length, resolution, and the distance you are from the targets when taking the photos. The PhotoModeler help file has a formula to help calculate an appropriate size. To start our project, we select Automated Coded Target Project from the Getting Started dialog. This first pane allows us to select a settings file. If you frequently perform projects with similar setups, these settings can be stored and loaded from a settings file, reducing the need to go through all the panes of the Automated Coded Target wizard. We do not have a settings file, so we click Next. This project was done using the 8-bit coded set, and the units are in feet. Click Next and browse to the folder where our images are stored. And add all the images. Click Next. A matching calibrated camera was found in our library. If you have not added your calibrated camera to the library, a wizard pane will allow you to load the calibration file. Click OK. Our project is a mix of coded and non-coded targets. These can be marked in stages if they are different sizes or if you want to have more control over their settings. We will mark them all on the first stage by selecting Sum. As coded targets are automatically referenced with each other, we are able to automatically run processing after they are marked. So we leave Processing Stage 1 checked. We will automatically reference the non-coded points next. A second stage of processing will refine the non-coded points during auto-referencing. If your photo set is suitable and you would like to refine the camera's calibration, you can run field calibration. For more information on field calibration, refer to the help file. We will use a known scale and rotation measured between coded points in the project. You can perform any of these operations manually as well, so in some cases you may want to only run a few of these steps, examine the results, and then run the remaining steps manually. We click Next. We have an approximate idea how large our targets are from looking at the images, and since we know there is not much noise in the image, we can allow a larger target range. We choose a maximum target size of 30 pixels and have lowered the allowed circularity to 0.6. This lower circularity is needed because there is quite a bit of perspective on some of our photos, causing the targets to look elliptical. If we've included more photos that had less perspective, we would not need to adjust this value. These values may take some experimentation with your particular project, but once determined for a project in camera, they should be consistent, making future projects easy to set up and execute. Knowing the separation of the dots and from previous experience, we use a search distance of 0.002 feet for auto-referencing. We set a translate based on coded point 21. And a scale. The measured distance from coded target 21 to target 14 is 7.6 feet. Set a rotation. Point 21 on the left to point 14 on the right, point 21 in the front to point 5 in the back. This is the final pane in the AutoProject wizard. We could enter a settings file name, and this would store the information we have entered for use in another project with similar setup. We click Finished, and the automated project starts running. The first stage is auto marking, where each image will be searched for targets that meet the target parameters we specified in the wizard. Processing was run using the coded target points found on the images. Now auto-referencing runs using the parameters we had specified, matching the non-coded points which were marked during the auto-marking stage. AutoProject is now complete and has found 359 3D points in the project. We close the dialog and see that all of our photos have been oriented. We open up a 3D view which shows the completed project with all of our points solved. These 3D points were all calculated with no manual marking or referencing. If we open up a photo, we can see which marks were found and used for the project. As with all projects, you should monitor the residuals and other quality indicators. The status bar here indicates the largest residual is 0.81 pixels, which is reasonable when all marks are targets. With careful setup, most projects will run cleanly with no errors, but with some setups the occasional error might need to be manually cleaned up. For example, if a coded target had been partially obscured. Our scale and rotation was set up during the auto project, so if we wanted, we could now perform measurements on these points or export the 3D model or point information for analysis in another program. We will now demonstrate 3 different techniques for creating a surface based on these points. First, as a point cloud. Use Region Select to choose the points of interest. Double-click to close the region, then select Create Point Cloud from Selection. Our surface is created, but PhotoModeler does not know which direction the surface should face. In this case, it has created the surface facing down. We select the surface and flip it so it is facing up. Open the Properties pane and select the surface. Adjusting the max U and V values of the point cloud surface will affect the fit of the cloud through the point set. We are adjusting the number of knots in the NURBS equation. Some trial and error may be necessary to trade off smoothness with forcing the surface through the point set. In this case, we will use 15 and 15. You can see the surface now fits the point set and accurately describes the shape. We will save this file as with pointcloud.pmr. This file is included in the tutorial projects. We will now show an alternate method of surfacing this set of points. We select our point cloud and delete it. As we don't want to include the targets on the ground, again we use Region Select to identify which points we are interested in using to create the surface. Alternately, we could have separated the ground points into a different layer and hidden them. We choose Automatic Surface Triangulation. Select 2.5D Surfacing and pick OK. This has created individual triangular surfaces between our selected points. If we turn off points, we can see the triangulated surfaces. We select all the surfaces and turn off their double-sided property. These triangles have also been created facing down just like our point cloud. We use the flip surface command so they face up. Then we set their smoothing group to 1 so they all share the same smoothing group. The surface normals will then be calculated to show a smoothed surface. We will save this file as autotriangulated.pmr. We will delete the triangulated surfaces so we can demonstrate a third surfacing method called lofting. To create a loft surface, we first need to create curves to loft through. We will use the Curve Through Points tool to create ribs in our point set. Points can be selected on the 3D viewer or on photos. We will use a combination of them to create this first curve. And the last point here. Right-click, End Curve Draw. Now we'll start the second curve. Right-click, End Curve Draw. The third curve. Here we have finished creating curves through our points. We turn off points and select Loft mode, then select the curves to loft the surface through. Choose Finish Surface, and a lofted surface has been created upside down. We'll flip the surface, and our lofted surface has been created. We will save this file as loft.pmr. In the previous section, we showed a fully automated method for producing a point cloud model. Now we will demonstrate the automatic tools used independently, instead of all tied together in an AutoProject. We'll first show auto marking and then auto referencing. This is useful if you do not have the coded target module, or for performing each step of an AutoProject individually to help find errors or help fine-tune automated project setups. To show how to run the automatic tools directly, we will select a region of points, delete them, and then recreate them. We use Region Select and choose a set of points to delete. Select Delete. Delete marks on all photographs. You can see the marks in this section of the photo, and all other photos are now deleted. To automatically detect these targets, we select Automatic Target Marking, which brings up the Auto Marking dialog. The settings here control what targets will be detected. The less noise in an image, the more lenient these values can be without marking invalid targets. By noise, we mean parts of the image which appear similar to a target but are not intended to be a target. For example, bolt heads, circular oil spots, etc. Projects that use retroreflective targets, that is, targets with a special material that is very bright when hit with a flash, are very high contrast and with little noise. These projects are easier to automate due to the wide range of parameters that produce successful results. We can control which photos will be marked. In this case, the marks have been removed from all photos, so we select All Photos. You can mark only a specific region of an image or the entire image. We will mark the whole image. Target identification will be done automatically. We will leave the new marks on the default layer. The target marking parameters are the important settings for controlling which targets will be identified. The maximum diameter should be the size of the largest target in the image. We click here to select the region defining the largest target. We zoom in and select a region around our largest target. The target diameter is set to 23 pixels. The minimum target size is a percentage of the largest target. Depending on the range of target sizes, perhaps due to depth variations in the photo, this value can be adjusted. The target shape controls how circular targets must appear in the photo. All of your targets should be circles, but due to perspective, they may appear elliptical. The lower the number, the more elliptical targets are allowed. This parameter also helps weed out non-targets such as small rectangular blobs. Because some of the targets in our photos are coded, we will select Some. If there were no coded targets or you do not have the coded target module, you would select None. If you only have coded targets in your project and no regular targets, you can select All. This will be the most reliable type of target identification, as image noise rarely matches a target and its code ring. We select Mark Points and the automatic target marker starts running. Target marking is now complete. All of our images have been searched and any targets within our parameters have been marked. The summary shows which targets were found on which photos. You can see the targets have been detected, but their marks display in gray because they have not yet been referenced. The codes on any coded targets allow them to be uniquely identified in each image, so they are automatically referenced during the marking stage. To calculate the 3D positions of non-coded targets, they must be referenced. We could manually select these marks and reference them with the other images, or use the automatic referencing tool. Automatic referencing requires a well-oriented set of photographs. We have already oriented these photos, but if you are starting the project from scratch, without coded targets, you would need to manually reference sufficient points for the project to process. Once the project has processed and the photos are oriented, you can use automatic referencing for the remaining points. The settings on the automatic referencing dialog control which points are considered for referencing matches. If there are incorrect references being made, you can adjust these to reduce the errors. For example, only using a subset of marks by separating them into layers. A larger search distance means the areas searched for marks will be greater. The default distance is usually a good place to start, but if you find points are not being referenced, you can increase this distance. If misreferences are being made, reducing this number can help. 3 photos is the minimum number for a point to appear on for automatic referencing to work. If there are more than 3 photos, the additional redundancy will help reduce mistakes. We leave all defaults and choose Execute Reference. Auto-referencing is finished, and we can see 255 marks from single photos were combined to form 32 new points on 4 or more photos, and 1 point on only 3 photographs. We close the auto-referencing dialog and can see all the matches have been made and the 3D point locations have been solved. If a large number of points were added by auto-referencing, it can be a good idea to run processing so these points are refined and used to adjust the camera positions. This concludes the Automatic Tools tutorial. We have learned how to use coded targets and the AutoProject wizard, create point clouds, auto-triangulated and loft surfaces, run auto-marking and auto-referencing directly,